Okay, this is going to be a Newton's second law accounting for friction example problem. This is the problem, and I chose this problem because it has a certain level of complexity. You have to do some problem solving, but also it's simple enough that I can focus more on physics than on all of the algebra and the maths you have to do with it. So two blocks are connected by a massless rope over a massless, frictionless pulley, as shown in the figure. The mass of block 2 is m2 is equal to 10.5 kilograms, and the coefficient of kinetic friction between block 2 and the incline is mu k is equal to 0.2. The angle theta of the incline is 27.5 degrees. If block 2 is moving up the incline at a constant speed, what is the mass m1 of block 1, and what is the tension in the rope? So, our first step, as with all physics problems, is going to be drawing a freed body diagram of every moving object. So here we have the forces that are applying to block 1, which is only going to be forces in the y direction. There are no forces in the x direction. And our forces applied to block 2. So first we're going to notice that the tension force applied by the rope is going to be equal on both blocks. And we're also going to notice that the tension force is going to be equal to the weight because this block is not accelerating. And all of the applied forces, the external forces, which tension is not an external force, are going to add up to 0 because there's no net force since the whole system is not accelerating, it's moving at a constant rate. So some more info on all of the forces involved. This is going to be our friction force, and it's going to point in this direction because 2 is moving upwards along the incline. This is going to be our normal force, which is the normal force that is applied based on the component of the weight of the block pressing into the ramp, and this is going to be another component of the weight of the block, which is the external force that moves this block this direction. That is the force of acceleration based on component of W2. So we're going to, now that we have our free body diagram, we're going to take note of what values we know and what that means. So since we know that, we're going to know that the weight of the block 1 is going to equal its mass times gravity, and since we're going to assume that this system is close to the surface of the Earth, that acceleration due to gravity is going to be 9.81 meters per second. And we know that W2 is also going to be equal to block 2's mass multiplied the acceleration of the gravity, which is going to be equal to 103 newtons. We know that theta is 27.5 degrees, and we know that mu k is equal to 0.2. Now that we have all of that, we need to ask a few questions. What is the magnitude of FAW2, and what is the magnitude of N? And those are going to be basically the same question, which we know because of this triangle. So since we know that this angle theta is going to be the same as that angle theta due to the law of triangles, we can use that in order to find the magnitude of this FAW2 force, since we know that it is a component of this weight, and we know that the angle that affects the components of this weight is theta. We can plug in and use some algebra to find that FAW2 is going to be equal to the sine of theta multiplied by 103, which is the weight W2. And that's going to equal 47.6 newtons. We follow the same steps to find that the normal force, which is the reactive force that opposes from this block the slope, is going to oppose the component of W2 to point that direction, and that's going to be the magnitude of which is going to be, like how FAW2 was sine, it's going to be cosine for a weight of 91.4 newtons is going to be its force magnitude. And this makes sense because 27.5 degrees is an acute angle, and it's on this corner. So this slope is going to be more wide than it is down. And since the slope is more wide than it is down, we would expect the upward normal force to have a greater magnitude than this downward to the side FAW2 force, which we see since the N is 91.4 and the FAW2 is 47.6. Now that we have the normal force, we can plug that into our kinetic friction formula, which is kinetic friction is equal to the normal force multiplied by mu k, which is 91.4 multiplied by 0.200 to be equal to 18.3. And now that we have all of these forces quantified, we can start to find W1, because we need to find W1 since it's the last force vector we don't know. And in order to find it, we're going to use the fact that the system is not accelerating so since we know that the system's not accelerating, meaning this counterclockwise and clockwise is not going to change the velocity at all. And since we know that all of the external forces are going to add up to 0. Or in other words, since W1 is in the counterclockwise direction, and Fk and FAW2 are all in the clockwise direction, FAW2 plus Fk is going to have the same magnitude as W1. And since we know FAW2 and Fk, we know that the magnitude of W1 is 65.9 newtons. And so I'm going to say that the counterclockwise direction is negative, and use the counterclockwise direction being negative, and this is an explanation of what I just said earlier, that since there's no acceleration, this force has to add up to this external force. So since the counterclockwise direction is negative, we're going to call W1 to be equal to negative 65.9, and since we know that it's negative 65.9, and since we know that the acceleration due to gravity is also going to be in the negative direction, and since we know that W1, as we said way back at the beginning, is equal to mass 1 times the acceleration due to gravity, we can use basic algebra to find that the weight divided by the acceleration due to gravity is going to be equal to the mass, for mass 1 to be equal to 6.72 kilograms. So that's the first part of the problem solved. Now that we have that part of the problem solved, we can work on what the tension force is. And this is actually pretty easy because we know that since this block isn't accelerating, and the other block isn't accelerating either, but since it's on an angle, it's more complicated, so I decided to choose the easier block to work with. Since we know that this block is not accelerating, we know that the net forces acting on just this block, excluding the rest of the system, have to be equal to 0 when added together. And once again, we're going to call, in this case, down rather than thinking about it in counterclockwise, is going to be the negative direction, and up is going to be the positive direction. But since there's no acceleration, the net force is going to be equal to 0, and the tension plus the weight is going to add up to 0, and the tension plus weight is going to be in the negative direction is negative 65.9 newtons. We know that the tension has to have the same magnitude in the opposite direction to be 65.9 newtons in the upwards direction, or in that direction for the other block, since we know that the tension force has to be equal since the rope has no mass. Now, since this was sort of easy, I decided to make it harder by including another problem in which there is acceleration. However, we're also going to say still, and we're going to just pretend that this block happens to fit with whatever numbers we have here, because this block has to fit with whatever numbers we have here based on the truth we have. if this block happens to accelerate, in this case downwards at 3 meters per second, that block has to also accelerate at 3 meters per second, or the rope will snap. So ignoring everything that's over here, as we're able to in order to find the tension, we're going to say that since acceleration is negative 3 meters per second, and we know that the mass of the object is 6.72 kilograms, and the weight of the object is 65.9 newtons in the downwards direction, we can use this algebra, which is net force is ultimately going to be equal to negative 20.2 newtons, because the net force is equal to the acceleration times the weight times the mass, and we know that the net force is equal to the acceleration times the mass because the acceleration is equal to the force divided by the mass, and so you just use basic algebra to find that the net force is also going to be equal to the acceleration times the mass, which is going to multiply to negative 20.2 newtons. So there is 20.2 newtons in the downwards direction of net force. And since we know what W is equal to, we can just add that together to find that the tension is only 45.7 newtons, which again makes it so that the difference between these is negative 20.2 newtons for 20.2 newtons in the downwards direction. And so the magnitude of tension is 45.7 newtons. The magnitude of W1 is 65.9 newtons, which makes sense because the magnitude of the weight being greater than the magnitude of the tension has to be true in order for this to accelerate downwards. And so that is a couple examples of Newton force problems, and including tension and acceleration and friction, focusing on the physics rather than focusing on the algebra to get there.